Howdy y'all, we're for Godspeed, and our project is the Gamma Detecting Rover. My name is Troy Baxter, I'm the team's project manager.
My name is Preston Banks, I'm the hardware lead and the assistant project manager.
My name is Trevor Rowe, I'm the electrical lead.
My name is Christian Ramos, and I'm the software lead.
Our team advisor is Dr. Lee, and our team sponsors are Jeff Scott, president of Northwind Portage, Heather Baxter, principal health physicist of Northwind Portage, and Robert White, principal engineer of LBYD. So, what do companies like Northwind Portage do? They focus primarily on investigating, remediating, and removing any and all radiological, hazardous, and toxic waste around the country. They primarily work with federal, state, tribal, and local governments. And the current project they're working on is a multi-million-dollar remediation project up in Canada. So how do companies like Northwind find radiation to clean up? Well, they send out a technician to walk up and down a field for several hours very slowly. While walking up and down the field, the probe has to be maintained around a height of 8 to 10 inches. So why might this be an issue? Well, a multi-million-dollar project is being dependent upon an inaccurate and inconsistent sets of readings, as you can see in the left figure. As a result, this causes an increased amount of time for companies like Northwind to spend on a project and an increased amount of money they have to spend overall. As a result, this results in the customer having to spend more money on something that may or may not have radiation in the area. Additionally, due to hazardous conditions, whether that be just the terrain itself or unknown radiation levels, the workers in the area are put at serious health and safety risks. So our mission is to provide companies like Northwind an affordable and reliable autonomous all-terrain gamma detecting vehicle that will save them time and money, and then also improve the worker health and safety overall.
How we aim to achieve this is by designing a rover that will be responsible for the transportation of the gamma radiation sensor. It would be collecting readings of approximately 8 to 10 measurements per square meter by implementing a proper movement speed and movement pattern. It would be holding the radiation detecting probe in between 8 to 11 inches from the ground, using a linear actuator and a pulley to manipulate the probe height for whatever is required at that moment. We'd also be using a sensor mechanism to determine the distance between the ground and the base of the chassis, so we know what height to adjust the probe to continuously get accurate readings. We would be implementing a full autonomous mode, complete with obstacle avoidance, so that should ideally be able to complete the entire specified route with no human input after initiation. Although we would also incorporate a manual mode in case the autonomous mode happens to fail or encounter some sort of obstacle that it cannot get around by itself. Here you can see the general motion pattern. The path would be designated by the technician, and whenever an obstacle is detected, it would go ahead and traverse around the obstacle and get back on its initial assigned path of motion.
So the requirements laid out by Northwind for us to follow when we would develop this rover, that it needs to be capable of both autonomous and remote operation. Needs to be able to traverse a slope of or slope of 3 to 1 or about 18 degrees. Must be able to operate for at least 2 hours. Have a course or route inputted by a technician, and then follow that pre-programmed course while avoiding obstacles. And then in the event that the rover becomes stuck, it hits a slope that is greater than 3 to 1, there's some sort of unavoidable obstacle identified, or the battery is low, it is to alert the technician. And then of course it will have the probe height controlled automatically, or if need be, manually as well.
So the concept of this rover, there's 3 main components. One of the components is going to be the technician computer, or the ground station that the technician uses. The next component will be a Raspberry Pi and the Pixhawk controller, which is connected to the rover. So the technician will have an application called Mission Planner, which sends signals and commands to the Raspberry Pi, and the Raspberry Pi acts as a network bridge between the technician and the Pixhawk, and it's a Wi-Fi based signal. So the technician will send the commands through Raspberry Pi, which will then be sent to the Pixhawk, and that's how the rover is controlled. Now on the Pixhawk, there are the sensors and the piston and the cameras that are controlled through the Pixhawk, and that data will be sent back to the Raspberry Pi and then back to the technician.
This will weigh in total approximately 80 pounds. Most of our components will be housed in a 12-inch by 12-inch by 30-inch aluminum toolbox that will be fully weatherproofed. We will be using a 30 amp hour 12 volt lithium iron phosphate battery. After our calculations, this should give us about a 3-hour runtime in between charges. And we chose a lithium iron phosphate battery because it is both lighter, more energy dense than a lead acid battery, while also being a bit cheaper than a lithium ion battery of the same voltage and capacity. We'll be using 4 12-volt right-angle DC motors, each of which consume about 1.6 amps and are just under 5 Newton meters of torque. This should give us more than enough torque to go ahead and be able to traverse our rover throughout all the types of soil that we will be encountering. We're going to be using a Pixhawk 4 microcontroller as well as a Raspberry Pi to control and communicate all needed information, using a LiDAR for obstacle avoidance purposes, and using a camera both for obstacle avoidance as well as giving the technician vision whenever it is in manual mode. The sensors, the gamma radiation sensors, are going to be what is used by Northwind Portage, our sponsor. The 11-2-2-1 rate meter you see on the far right, which will be housed inside of that toolbox. The 11-44-10 Gamma probe, which is what we will be just moving up and down depending on the height relative to the ground. And the Trimble GPS unit, which is what they use to go ahead and store the location of the readings on the map that you've seen prior.
For the software, the main software program that's going to be used will be the ArduPilot Mission Planner. This Mission Planner application has autopilot and route planning capabilities, which means that you can go and create various routes and various route plans within the program. If you look at the program to your right, that's a general view of the GPS around the Zachary Engineering Building. This application can also control the rover hardware to run according to the route specifications. So that means that the rotors will be controlled, or the motors will be controlled based off the route and based off where the rover needs to go next. This application also lets us see the sensor output for the Pixhawk's 4 sensors. This includes the accelerometer, velocimeter, and etc. And it also enables live video stream through the camera and also controller joystick input for manual control. The other software that we're going to be using will be the Raspbian operating system that will be connected to the Raspberry Pi. This will help us make that network connection between the Pixhawk and the ground station. And it also lets us send the signals to the Pixhawk from Mission Planner or vice versa to let the rover do the actions that it's required to do. So for the functional block diagram, on the far right, we have the Mission Planner application that will send the Mission Planner commands to the Raspberry Pi, and the Raspberry Pi will send those commands to the Pixhawk. And then the Pixhawk will send all of its data from the sensors and all the other components connected to it back to the Raspberry Pi, and then the Raspberry Pi will send that to the Mission Planner application. Now connected to the Pixhawk, we have the LiDAR, the camera, the accelerometer, velocimeter, all of the different types of signals that will be used to control the motors. This includes the signals sent to the H bridges, to the radio cellular system, to the camera, and vice versa. All of these will be powered using a 12-volt battery, which is controlled through a power control system. And then we have a power management board in order to give all the devices the required voltage and amps that they need.
So our work breakdown structure can be broken down into 3 distinct sections: the project management section, the hardware section, and the software section, with the hardware section being broken down into 2 subsections, mechanics and electronics. Now, to be clear, these do not specify everyone's specific workloads. It just means that the lead for each section is responsible to make sure all work done in these sections are completed. So for the project management section, this could be broken down to 5 different areas. The scheduling, which includes the Gantt chart and any and all meetings that we have, whether that be with sponsors, with ourselves, reports, so any reports dealing with Capstone, documentation, such as user manual and technical documents that will be sent to Northwind next semester, and then project manager documents, hours logged, and then intellectual property documentation with Northwind. Funding and budget is another section. That includes purchases through ETID, funding acquisition with Jeff Scott, and then A&all treasurer duties. And then finally, the sponsor advisor communication, that would deal with just generally talking with them, making sure they're up to date through slide decks, videos, and media.
When looking at the mechanical section, it can be divided up into 5 subcategories as well. The motors include motor insulation, the wheel system. We have the wheels, the shocks, and the supports for the wheel system. The chassis has the chassis supports as well as base plates, housing, battery holder, and speaker holder. These 3 will likely be done in tandem during the build rover phase. Following that will be the probe system to include building the probe holder, the probe controller, and integrating with the GPS and probe reader holder. Finally, for the mechanical side of things, we'll have the environment proofing to include protective casings, water resistance, lead paint protection on the bottom of the rover to protect it from the gamma radiation, as well as heat protection, given that these are sensitive electrical components in an aluminum box.
For the electronic aspect of this, we have the control board assemblies. This includes both the manual controls as well as the sensor controls, component wiring, which involves making sure everything is properly powered, properly connected to the power source, and making sure that all components are properly wired together. The motor control, which includes the connection of the H-bridge to the motors and the connection of the H-bridge to the power source, and connection of the H-bridge to the microcontroller so that we can properly control the movement pattern, movement speed. The probe system, which is going to be the linear actuator and pulley system, making sure that that is properly wired and properly connected to the before mentioned Raspberry Pi and Pixox so that we can manipulate the height as we need. All of our sensors, including a humidity sensor, a voltmeter, the LiDAR, accelerometer, velocimeters, and camera, making sure those are properly connected and properly configured. And the alert system, which we plan to implement, which will be using LEDs and speakers, just as another way to let the technician know whenever it is encountering something that will need human interaction.
For the software structure, we have the manual control section, which includes the live stream to the technician via the camera, and we also have to take in the inputs from the various sensors that will be from the Pixox sending back to the technician. The next section is the probe position control, which is just the programming the probe height, and also PWM signals can send to that probe controller. The next section is the motor control, which includes the PWM signals sent to the motors, the ability to move forward, backwards, and turn, and for the motors to help the rover drive straight towards the reload station once all the routes are completed. The next section is the sensor data, which includes the voltage readings for the batteries that are inputted, the humidity warnings, accelerometer data, velocimeter data, and the gyroscope data. The next section is coordinate mapping, which includes route planning, coordinate storing, and this also includes all the property boundaries, the major obstacle locations, and the refueling station within the mission planner. The next one is obstacle detection, which is from the LiDAR and from route planning. And then the next and the final one is the technician alert system, which is the LED and the audible alert systems.
Looking at the responsibility assignment matrix, this is broken up into 5 categories. The first one being initiation or concept phase. This is most of the administrative work and will be done by myself and Troy. So going into the planning phase, this is where we kind of get into the nitty gritty of things. Being the hardware lead, I'll be taking control of the designing the probe holder, rover body, wheel structure, then determining the parts required for the chassis, the shocks, and wheels. Trevor, as the electrical lead, will be handling the sensor selection as well as determining the motors and batteries used, as well as the battery pricing. Christian, as the software lead, will go ahead and determine the control board and software selection, and this will all be monitored and signed off by Troy. Going into the third phase, we have construction or the execution phase. Again, being the hardware guy, I will be dealing with building the rover body, suspension, the accessories, and the probe holder. The Trevor will take over with the installation of the batteries, sensors, control board, and the power control board. And then Christian will go ahead and handle building of the software programs, as well as integration for the probe control software, obstacle detection, route mapping and planning, motor controllers, sensors, and building the alert system. Moving on to the testing phase, this will include getting the raw data for the probes and the sensors, testing the rover on a flat surface, on a hilly surface for obstacle avoidance, and then for the short test during over an area of about 50 square meters, and then during our long test where we plan to operate the rover for 2+ hours. This will require all of our participation, however, will be signed off and methodology controlled by Troy. And then during the closing phase, we have the rover technical document and user manual. Those will be headed by myself and Troy, and primarily for the use of Northwind as our sponsor. And then final report and final presentation will have all of us participating as to be expected.
So our schedule can be broken down into 12 distinct phases as outlined by the network logic diagram. These phases can be broken down into 3 larger categories in themselves: the manual operation, the autonomous operation, and testing. So for manual operation, that's phases 1 through 3. That includes just building the rover, any basic movement through a controller, and then height sensing and probe controls. For the autonomous phase, this will be level 1 autonomous movement. So just going straight point to point, making sure it follows a specific route just we laid out. Obstacle detection is phase 5, and then including warning systems is phase 6. Phase 7 is level 2 autonomous movement, and then that's just avoiding any obstacle detection. And then the last phase for this section is just level 3 autonomous movement, which is route planning. And that's where we incorporate everything we want and make sure everything's correct before we go into short-term test. In the testing phase, that's short-term test, which is just 50 square meter area, where we check to see that readings are accurate, that it's going in a straight line, and that it's in general better than what a person can do. Then we go on to cosmetics, protective equipment, and final debugging before we go into the long-term test, which is 2+ hours, but it really is just until the battery dies. And that's to see if anything long-term pops up that we didn't expect. And in the final section, final phase is just finalization. That's final demo, final reports, anything that we need to get finalized for the completion of ESET 420. So our schedule can be broken down in this Gantt chart, as you can see with the schedule. We hope to get all the manual operation stuff out of the way by December, by the completion of the semester. For phase, we're currently just finished phase 0, which started back in August and is completed with our first round of purchasing. And then phase 1, that starts with the building of our rover, which we're currently waiting on to do once we get the parts in. And then that's going to end with the installation of all key components. Phase 2 will be the configuration of board and radios, and it will end with a successful just moving the rover back and forth and making subtle turns. And then finally for phase 3, it's building the probe control and making sure it's correct.
So the assumptions going into this that we used for our calculations and our design was that the rover would operate in a 2,000 square meter area. So some of the assumptions that we'd be going off of are that this rover will be operating in an area of 2,000 square meters. The soil is expected to be type C or better. This could include gravel or sand. There's going to be no greater slope than the 3-1 slope, or about 18 degrees. Operation will not be conducted in inclement weather. This would be a good opportunity for the rover to be set into manual control and be driven back to the technician. And then it must be slow enough that it can get 8 to 10 data points per square meter as well. Some of the limitations that we're going to face are that the technician must be within 100 meters for manual operation. The rover is going to be designed for a maximum obstacle height of 4 inches. It should be expected to go 2+ hours on a single charge with battery, and it must be able to move approximately 0.4 miles per hour while detecting. Going into the risk assessment matrix, we have on the bottom the level of impact, and then on the left-hand side, we have likeliness to occur. The most insignificant is going to be minor illness. We are around a bunch of people, and that is definitely something that could happen. Common cold is going to be here. There's a lot of people. It's kind of to be expected. More marginally, we have something such as COVID. This is going to be this is likely going to limit us due to a quarantine period being necessary. And then also seldom to occur would be a software incompatibility issue. We've done a lot of planning and just a lot of calculations going into this, so it shouldn't happen, but it is still always a possibility. And then because we are in Texas, there could be extreme weather just popping up out of nowhere. Moving over into moderate, there could be some sort of injury. We'll be using the FEDC, but we'll be out in the world as well. Some of us have jobs, so there could be some injury occurred at some point. This can definitely set us back because we'll basically be losing a body. And then unlikely is going to be vandalism as well. This could just be any action with ill intent towards either us or our rover. We really don't know who would want to, but it is something that can happen, and it's best to be prepared. And then for critical, we have parts don't ship in. This is something we've ran into the issue, and luckily we've been able to remedy. But being that we are dealing with several shortages, it could be a very potential hazard, and it could drastically lengthen our time to completion. Also, with anything electrical, especially programming, there is possibility for software crashing. Depending on where we are, if we might need to order new parts, might need to reorganize, that is something that can definitely go. And then on catastrophic, we have crucial component breaking. This could be anything from the DC motor giving out to frying of the electrical components. Once again, it's likely not going to happen, but it could have catastrophic issues. And then looking into the unlikely category, we have funding issues. This is definitely probable. So it's just something that we got to handle as we go.
Impact the world outside of Texas A&M University. Well, this will be reducing human exposure to gamma radiation, making it so that the technician does not have to do such a mundane task that puts them in harm's way, essentially exposing them to more radiation than ideally anyone has ever really wants to be exposed to. This also increased the reliability of the reading, speeding up the entire process. Speeds it up by making the first batch of readings much more accurate, reducing the need to go back and redo the readings at cost to both the company and the taxpayer, because they're the people who ultimately pay for this. There's also benefit the company in that they don't have to pay the technician to do that mundane, boring, dangerous task, and that technician can instead focus their efforts on something more worth their talents and more worth their skills. In short, this is exactly what automation is for: increasing safety, decreasing the human involvement in tedious, low-skill tasks, and just making everything run a little bit faster and a little bit more efficient.
So in conclusion, we intend to save companies like Northland Portage a bunch of time and money, while also improving the overall safety and health of on-site workers through the development of this autonomous all-terrain gamma detecting rover. We thank you for your time, and if you have any questions or comments, please leave them down below.